So in this problem here, we're asked to take each sum and express it in terms of the variable n, where n is some number. So here we have the sum as k goes from 1 to n of 4k minus 2. So much like we did in the previous example when we were doing that sum up to 200, we can now go in and say, hey, I can break this sum up using my sum properties. So the 4 can be pulled out, and I'll have 4 times the sum of the k, it's a k, as k goes from 1 to n, minus 2, the sum of 2, as k goes from 1 to n. Or if you wanted to factor that 2 out and have sum of 1, then you could do that as well. And then for sum of the k's, sum as k goes from 1 to n of k, we can use that formula. So that's going to be 4 times the sum of the k's is n times n plus 1 over 2. This time we're going to be sticking with n. We're not plugging a number in because we don't know what n is. And then 2, that would just be minus 2n. Okay, and then we go through and do a little bit of simplifying. The 4 and the 2 will cancel out, so we have 2 times n plus 1 would be 2n squared plus 2n minus 2n. And so all that is actually 2 times n squared. So if you start computing that term for different values of n, like if you wanted to work it out by hand for n equals 4, then this is saying that's going to be 2 times n squared. So 2 times 4 squared would be 16, would be 32. And so you kind of play around with that and see how that works out to actually give you 2 times the square of whatever n is. If you just kind of practice a few of them. Let's consider a second one. Here we have the sum as k goes from 1 to n of k squared plus 3k, all that divided by n squared. Okay. So I can break that up by distributing the n squared into both things in the numerator. And then what I want you to realize is n squared, the n squared here does not have anything to do with the index variable. Okay, so n's not a variable in terms of the sum. Okay, k is my only variable. So what that means is when I break this apart, I can pull that 1 over n squared out, and I'm left with 1 over n squared times the sum of the k squareds, as k goes from 1 to n. Plus, I can take that n squared and put it with the 3k, so I can pull out a 3 over n squared times the sum as k goes from 1 to n of k. And at this point, we then just need to invoke our formulas. We just need to invoke our formulas for the sum of the k squareds and the sum of the k's. So sum of the k squareds, that's n times n plus 1 times 2n plus 1 all over 6. And that's all going to be multiplied by 1 over n squared. And then 3 over n squared times the sum of k. That's n plus 1 over 2. And then we just go through and we start doing some simplifying. So the n there will cancel with the n squared to leave just an n in the bottom. Then if I multiply the stuff on top out, n plus 1 times 2n plus 1, I'm going to get 2n squared plus 3n plus 1. All of that's going to be over 6n. And then if I go to the other sum there, the n will cancel with the n squared again. I'll have 3 times n plus 3, all that over 2n. And then that answer is expressing it in terms of n, but let's go a little bit further and simplify some. So 2n squared over 6n, I can cancel out the n, and I'll have n divided by 3. The 2 and the 6 will also cancel. Then I can go to the 3n over 6. All right, the n's will cancel out, and I just have 1/2. And then I can have 1 over 6n. And then 3n over 2n. The n's will cancel out, and we get 3/2. And then 3 over n, 2n would just be 3 over 2n. And then I'm just going to go one last little step here and simplify. So I have n over 3, I have a 1/2 and a 3/2, which will become just 2. and I have 1 over 6n plus 3 over 2n. So here I would need to get a common denominator for the 6n and the 2n. So I could multiply the last fraction here by 3 in both the top and bottom. That'll give me 9 over 6n plus 1 over 6n. 9 plus 1 would be 10. So I would have 10 over 6n. But 10 over 6n will simplify to be 5 over 3n. So we have n over 3, and again the 1 over 6n and the 3 over 2n becomes 5 over 3n, and 1/2 and 3/2 becomes 2. Okay, and so now we've expressed that in a nice formula in terms of n that we could now evaluate for any value of n we wanted to deal with.